In Chapter 1.5, we're going to discuss applications of quadratic equations. I would like you to review in your book pages 148 through 154 and go through a few examples. We're going to go through a few examples in this video. Our main objectives are going to be looking at geometric problems. I'm going to have an example of the Pythagorean theorem. We're going to use quadratic models to solve a problem, and then we're going to look at a motion problem. So in our first objective of a geometric problem, this is problem number 26 on page 155. The front face of a house is in the shape of a rectangle with a queen post roof truss above. The length of the rectangle region is 3 times the height of the truss. The height of the rectangle is 2 feet more than the height of the truss. If the total area of the front of the house is 336 square feet, determine the length and width of the rectangular region. So the first step, of course, is to draw a picture that gives us a clue of the information that we need to have. And then in blue, in the box blue, we have our strategy. The total area is equal to the trussed area plus the rectangular area. The trussed area is nothing more than a triangle, so it's the base times the height divided by 2. This gives us 3/2 x squared. The rectangular area is just the length times the width. In this case, it's x plus 2 times 3x, which is 3x squared plus 6. Now, we're going to take all that information and put it into our equation. And so the information of 336 comes from the total area of the front face of the house. And then we put in the rest of the equation, 3/2 x squared plus 3x squared plus 6x. Now, the first step is to get rid of the fraction. I'm going to multiply both sides of the equation by 2. That gives us 672 is equal to 3x squared plus 6x squared plus 12x. Now I'm going to use the zero principle. I'm going to bring the 672 over to the other side of the equation. That means I subtract both sides by 672, and I end up with 0 on one side. This is using the zero principle, of course. And then I'm going to divide by 3 to make the numbers easier to work with. I divide by 3 and I get 3x squared plus 4x minus 224. I see that 224 is factorable. One of the factors is 28 times 8, and I notice that 8 times a negative 3 is certainly 24, a negative 24, and 1 times 28 is 28. If I add those together, I get 4, which is the middle term of my equation. So it's factorable, and so I can factor it into 2 pieces. I get a factor of 3x plus 28, and I get x minus 8. So the only possible dimension is positive, so x is equal to 8 is my answer. And so then my dimensions for the length is 24 feet, and the height is 10 feet. In this objective, we're going to look at the Pythagorean theorem. So this is problem number 32 on page 156. The display area on a computer has a 15-inch diagonal. If the aspect ratio of length to width is 1.6 to 1, determine the length and width of the display area. Again, the first step in geometric problems typically is to draw the picture and put in the information. So here it is, and I notice that I have a right triangle in blue of my rectangular area of the computer display. 15 inches is on my hypotenuse, which is C in this particular case. A is going to be X, and then this is B down here is the length. So we notice that the Pythagorean theorem gives us our strategy. A squared plus B squared is equal to C squared. Now I just plug in the information into an equation. So I have x squared plus 1.6x squared is equal to 15 squared. I just expand that, and then I combine like terms. So I get 3.56x squared is equal to 225. And now I divide both sides of the equation by 3.56, and I get x squared is equal to 63.2022. And now I take the square root of both sides of the equation, and here I will not have a minus. Usually when I take square roots I get a plus or minus, but the minus doesn't make any sense because length cannot be negative. So when I take the square root I get 7.94998, and I'll round it to 2 decimal places, and when I do that I get x is equal to 7.95 inches. So my width is 7.95 inches, and the length of the computer screen or display is 12.72 inches. So our third objective is to solve quadratic models. This is problem number 36 on page 156. The gas mileage for a certain vehicle can be approximated by m is equal to a negative 0.04x squared plus 3.6x minus 49, where x is the speed of the vehicle in miles per hour. Determine the speeds at which the car gets 30 miles per hour. So the hint is we're going to divide through by negative 0.04. So here we set up the equation initially in the black. So we have 30 is equal to a negative 0.04x squared plus 3.6x minus 49. I'm going to divide through by a negative 0.04. When we do that, we get the following. A negative 750 is equal to x squared minus 90x plus 1,225. And now I'm going to use the zero principle, because the zero principle means that I can solve a quadratic equation for the variable. And so I set up the zero principle. So 0 is equal to x squared minus 90x plus 1,975. Well, how did I get that? I added both sides of the equation by 750. Now, I'm going to use the quadratic formula. I'm not going to factor this thing because it's not really factorable. So now I put it into the quadratic formula. X is equal to 90 plus or minus the square root of 90 squared minus 4 times 1 times 1975 divided by 2. That is the formula for the quadratic for x in this particular case. X equals 90 plus or minus the square root of 8,100 minus 7,900 divided by 2. So x is equal to 90 plus or minus the square root of 2 divided by 2, or 90 is equal to, or x is equal to 90 plus or minus 10 divided by the square root of 2 over 2. So x technically is equal to 45 miles per hour plus or minus 5 times the square root of 2 miles per hour. Well, we don't really know what that is, so we go ahead and do the arithmetic, and we get a solution of the following: 52.07 miles per hour or 37.93 miles per hour will give us the gas mileage of 30 miles per gallon. Our final objective is to solve quadratic motion problems. So one of the motion problems happens to be a skill practice number 5 on page 154 in your book. A fireworks mortar is launched straight upward from a pool deck 2 meters off the ground at an initial velocity of 40 meters per second. The first thing we want to do is write a model to express the height of the mortar in meters above the ground. So we want to note that the gravity is equal to 9.8 meters per second. So to do that, we write out h in terms of t. H is equal to a negative 9.8 divided by 2, t squared plus 40t plus 2. This formula is in your book in terms of how to write the motion of a projectile going into space. So now we can rewrite this as h is equal to a negative 4.9 t squared plus 40t plus 2. The next question is, find the times at which the height is 60 meters. So we want h to be 60, and in our equation 60 is equal to a negative 4.9 t squared plus 40t plus 2. So I like to get this to the 0 to see if I can factor it, or I can use the quadratic equation. So to do that, I'm going to divide both sides of the equation by a negative 4.9, and when I do that, I get the following equation: a negative 12.248 is equal to t squared minus 8.163t minus 0.408. So now we're going to set up the zero principle. So we add both sides of the equation by 12.248, and we get the following: 0 is equal to t squared minus 8.163t plus 11.84. And we put it into, of course, the quadratic equation, and we get t is equal to 8.163 plus or minus the square root of 19.27 divided by 2. And so we get t is equal to 6.28 seconds, or t is equal to 1.89 seconds. So part C and D is something that is not directly in the book, but it asks you, does the mortar reach 100 feet? So we want to find out, well, how high does it actually get? So there is a formula to find out the maximum height is at a certain point, and for a quadratic equation, the formula for finding what t is, the maximum height at t, is when x is equal to a negative b over 2a. So in this case, we're going to let t equal a negative 40 over 2 times a negative 4.9. That gives us the maximum height is attained at 4.08 seconds. Now we want to find t, so we plug it back into the equations, or the equation, and we get h is equal to a negative 4.9 times 4.808 squared plus 40 times 4.08 plus 2, and we get a maximum height of, there it is, 83.63 feet. So it doesn't ever reach 100 feet. How long is the mortar in the air? Well, the height has to be 0. So when it's no longer in the air. So there it is. We set this equation equal to 0. We divide through by negative 4.9 and we get 0 is equal to t squared minus 8.163 minus 0.408. We plug that into the quadratic equation and we get t is equal to approximately 8.2 seconds in the air. So that concludes our applications of quadratic equations.